Hey everybody, thanks for tuning in. So this is going to be part 4 of our video lecture series on galaxies. And in this video lecture, we're going to be talking about dark matter, the invisible component of galaxies, and why we think it exists. Okay, so before we begin here, I do want to point out some specific details about this opening slide, because it is pretty informative. And so if you look at this picture, what you're seeing here is basically a galaxy cluster, which is a group of galaxies that are all gravitationally bound together. And so this purple-violet glow that you're seeing near the center is where we think that dark matter actually exists within this cluster. And then the last point of detail that I want to point out is if you look at the center and then now look at the edges around that center, so basically like right here, or there, or here, you can see distorted arc-like structures that appear to be wrapping around this central galaxy cluster that you're seeing in this picture. And that's definitely something that we're going to talk about in this video lecture, so stay tuned for that one. And then lastly, I do want to issue a disclaimer. So dark matter is a very active field of research in astronomy because we know so little about it, what it's made of, where did it come from. And so whatever information that we learned from this video at this time of recording, which is 2020, it might be updated in the next coming years. So again, that's just how science works. Scientific knowledge is provisional. So with that being said, now let's jump right in. Okay, so a little bit of a history lesson here in terms of how we came to know about dark matter. It all started in the 1930s. So Fritz Zwicky, he was a Swiss astronomer. You can see a picture of him here on the left. You can see that he has quite a personality. His colleagues actually thought of him as a very eccentric person. What he did was he measured the masses of the galaxies in this cluster of galaxies called the Coma Cluster. And so the Coma Cluster, it's about 1,000 galaxies bound together, and it's about 300 million light years away. So it's actually relatively pretty close, considering that clusters could be billions of light years away from us. And so what he did was he actually measured the mass in two different ways, because after all, if you're measuring the same thing in two different ways in a perfect world, you should get the same exact number, right? And so method number one was he thought that, hey, if you're actually seeing the light coming from these galaxies, the light from those galaxies should be able to tell you something about how massive those galaxies are. So you can just add up all that light, and that should also give you a number for the amount of mass contained within those individual galaxies. And you just add them all up and you get the total mass. So essentially, the luminosity is related to the mass, right? Mass follows light. Number two is by observing how these galaxies are moving relative to each other. Because if they're moving fast and they're still gravitationally bound to the cluster, that means that the cluster itself has a large amount of mass, means it also has a strong gravity in order to keep those galaxies bound to the cluster. And so what he got from measuring the mass from two different ways was that the gravitational mass was calculated to be 400 times greater than the mass coming from the light. And so there was a huge disagreement between those two methods, and therefore he concluded that most of the matter that are contained in the galaxies is invisible. We can't see it, so therefore it must be dark. Hence the term dark matter. And so unfortunately, because Zwicky was also notorious and had a reputation for over-interpreting results, no one really believed him at the time. And so it wasn't until about 40 years later, in the 1970s, Vera Rubin, she was an astronomer that was studying the spectra from different spiral galaxies. So interestingly enough, she actually did a lot of her research in Palomar Observatory right here in San Diego County, and she was actually the first woman to be admitted in that observatory. So she was also breaking social barriers at the same time. And so she was measuring how fast stars were moving away from the center from these galaxies. In other words, she was actually forming rotation curves. And so she did also studies on the Milky Way galaxy, which is going to be our next big topic here. So what you're seeing here is a rotation curve for the Milky Way galaxy. So in order to understand the significance of this graph, we actually have to explain the different components. And so again, in the vertical direction here is a rotational velocity, which means this is how fast stars are orbiting, and it's plotted against the distance from the center of the Milky Way. So basically, right here is going to be the center of the Milky Way, and as you're going further and further and further away, this is measured in light years, you can see how fast stars are orbiting from the center of the Milky Way. Okay, so the first thing I want to do here is actually explain to you the red calculated curve, okay? Because that's what you would predict from Newton's law of gravity. And so what you have to realize here is that the speed of the star's orbit, in other words, the rotational velocity measured in kilometers per second, is going to be related to the enclosed mass within their orbit. And so you have a star orbiting around the center, and so whatever the mass is enclosed there, that's also going to play a huge role in terms of how fast those stars are going to be orbiting. So in other words, the larger the enclosed mass, then the stronger the force of gravity, and that translates into the stars having to move faster to stay bound. And then also, you know that gravity depends on another variable, which is distance. We learned from Newton's law of gravity that the further away you are from whatever mass is close to you, then the weaker the force of gravity. So in this case, the further the stars are from the enclosed mass within that orbit, then the weaker the force of gravity. Okay, so knowing those, it's a little bit of a review, I know. Then we can pretty much figure out how to explain this red curve. Okay, so in this case, let's look at the central bulge. We see that as you're moving away from the central bulge, the faster stars have to move from the center of the Milky Way galaxy. And that's because the stars in the central bulge are clumped together. In other words, it's the densest part of the galaxy. So as the distance from the center goes up, so you're getting further away, the rate at which gravity gets stronger with mass is larger or more dominant than the rate at which gravity gets weaker with distance. So therefore, you would expect stars to move faster in order to stay in orbit. Okay. And so now let's talk about what's going on in the disk of the Milky Way. So therefore, you're now in the outskirts of the Milky Way galaxy. So along the disk, the stars are a lot more scattered. So therefore, this part of the Milky Way is a lot less dense than the bulge. So as the distance from the center goes up, or it increases, the rate at which the gravity gets stronger with mass is going to be less than the rate at which gravity gets weaker with distance. So distance is the more dominant effect here. So therefore, stars are going to be expected to move slower in order to stay in orbit in the disk. Okay, and so now we can move on and talk about what she actually measured. So essentially, the theory, which is the red curve here, disagrees with the observation shown there in the white curve. The observed velocities did not agree with the theoretical or calculated velocities. And in a nutshell here, you can see that in the outskirts of the Milky Way, the measured speeds that the stars are orbiting are moving a lot faster than what was actually predicted using Newton's law of gravity. So this result had a lot of implications. Okay, so because stars cannot orbit that fast without something to pull them via the force of gravity. Otherwise, they would just leave the galaxy. And so, therefore, there must be some sort of invisible mass that definitely interacts gravitationally. However, they're not interacting via light, via electromagnetically. Also, we can conclude from Vera Rubin's result that the way that this dark matter is spread out is different from the way luminous matter, matter that we can see with our eyes, is spread out. Because you can see that if you look back at that previous result, near the central bulge, the measured is pretty much in agreement with the calculated or the theoretical, right? And so what we can conclude there is that the visible matter is the dominant amount of matter within the center of the galaxy. However, as you move further away, it seems like the matter that we cannot see is more abundant than the matter that we can see. And so at the time, Vera Rubin's result actually provided the strongest evidence for dark matter. However, in the recent years, there has been more evidence that's coming to light that supports this idea that dark matter definitely exists within galaxies. One of them is by observing the hot gas. And so just a little bit of a review. Whenever you have hot particles in general, remember temperature is a measurement of how fast these particles are moving within some sort of container. And so hot particles are going to be moving faster. And so now when you have hot gas within galaxies, in order for those gas particles to stay within the galaxy, you would expect them to be near the most massive part. Basically, that's where the gravity would be predicted to be strongest. And so here's NGC 4555. And you can see that there are two pictures taken here, and these two pictures are of the same scale. And so one picture here on the left is showing you the X-ray light, and the X-ray light is basically telling you where the hot gas is. And then in a visual, or the visible, that's telling you where the stars are residing within that galaxy. Okay, so if you believe that stars are the largest or most massive component of the galaxies, then you would expect that this would be where the hot gas should be located, because that's going to be where it's strongest gravitationally. However, looking at the X-ray, now shifting over to the left picture here, now you can actually see that the gas is definitely way more spread out than the stars are. And so they're located well beyond the visible light component of the galaxy. And so therefore, if that gas is still bound to the galaxy, there must be something keeping them there. And that something, we think, is dark matter. Here's another piece of evidence. So remember that opening slide where we talked about, in the outskirts of that cluster, there seems to be like arc-like structures. And so those arc-like structures are coming from the background objects within that cluster. So those objects are much further away. They're located in the background, whereas the cluster was located in the foreground. And so that, in fact, is called gravitational lensing. And so in Einstein's theory of relativity, he predicted, and also we've confirmed it multiple times now, that light actually takes curved paths. It bends around massive objects. So here's a diagram of that. So here is a massive object, and here's another object that's emitting light. So the light coming from this object will take a bent or curved path as it makes its way to go to Earth. And if it turns out that they're completely aligned along our line of sight as we look out further into space, then you're actually going to see a ring. That's called an Einstein ring. So it's going to be an arc-like structure. And so if you look at an individual galaxy, which is a pretty massive object in its own, then if there is a background object right behind it, you can see that gravitational lensing takes effect. So this is called the cosmic horseshoe. This image was taken by the Hubble Space Telescope. And this object right here in the foreground, that's about 3 to 5 billion light years away. Whereas this circular structure that you're seeing wrapping around this foreground galaxy is about 10 to 11 billion light years away. So it's much further away into the background. And so anyway, the point is, if you look at this picture, right, if you're believing that light definitely traces mass, then you can see that and probably conclude that most of the mass is concentrated within this region, in this like small nucleus of the galaxy. However, you can see that the light bending occurs much further away from that concentrated region of light in this elliptical galaxy. So again, there must be some sort of mass present that we cannot see that is responsible for, this lensing to be further out from the center of this galaxy. And then now let's talk about the bullet clusters. So these are essentially two clusters of galaxies about 3 billion light years away, so they're much further than the coma that we discussed a while ago. And they were recently just involved in a head-on collision with each other. So the gas, the dust, the stars within those galaxies all collided within each other, and also including the dark matter. Okay, so you can see some different parts of the picture here, and let me explain what they are. So the pink region here, it turns out that's where the superheated gas is observed, and we can see that through X-ray observations from different space telescopes. And the violet shown here, which is going to be located on the left side and the right side of these two clusters, that's going to be where we believe dark matter actually resides. And we think it resides there because of gravitational lensing. If you take a closer look from the background objects near the outskirts of these two clusters, like right here where I'm hovering with my mouse, and also here, you can see and observe those arc-like structures again. Okay, so there must be, again, some sort of invisible mass that's causing that lensing. And so the main and the key result from this collision is that the gas, the dust, and the stars and dark matter all behave differently in a collision. Okay, so that's what you have to realize. And so if you watch this animation, so now these two clusters are basically colliding. This is a simulation of that event. See, the thing is, gas, they both interact electromagnetically. In other words, they interact using light, and also gravitationally, causing the gas to basically lag behind when those two clusters pass through each other. And that's something that we've already talked about when we talked about how light interacts with matter. It gets absorbed and re-emitted in random directions. So therefore, it's going to lag behind whatever is actually not interacting. However, now if you look at the purple or the bluish region, at least in this animation, because the lensing shows that the mass in the cluster actually lies further out in the left and the right edges, that actually suggests that dark matter does not interact with itself, which is really interesting because dark matter, it interacts gravitationally with visible matter. However, it doesn't really interact with itself. So it just passes on right through across that collision. Okay. So that's about it for the recent evidence that we've seen so far with dark matter. And so now let's ask a more important question. So let's say that dark matter actually exists. So how much matter can we see and not see? And this is where it gets a little bit depressing. Because if you actually calculate the dark matter that's present within the Milky Way and kind of extrapolate this for the whole universe, it turns out that 80% of the mass in the universe is dark matter. And 20%, the matter that we can see, or the visible matter, is only 20%. So that's only 1/5 of the total amount of mass in the universe. And it's a little depressing because for as long as astronomy has been around, the stuff that we've been studying is all within that 20%. And the stuff that we cannot see, that we only started recently studying, is all within that 80%. So yeah, we definitely have to do a whole lot more research when it comes to dark matter. All right, so that's about it for this video lecture. And in the next video lecture, now we're going to start venturing out in the grandest scales, talking about the universe as a whole. In other words, it's cosmology. So see you guys next time.